Let's just kind of work right from the book from the beginning here. So, one moment. Just read that for a moment, if you would. Just read that for a moment, if you would. Read the introduction there. Oh, I see. Hold on. Okay, hold on. Right. Okay, good. I wanted to deactivate the assignments because I don't want anybody working on them now, obviously. And I really do that, out of respect too for students. I mean, you're here in class, you're participating. When you participate and share your thoughts and ideas, it helps other students too. And so I don't want to, obviously, I don't want a student who chooses not to attend class to, be working on the exam at this time. It's not fair to you all, or even assignments. So, okay. So, eigenvalues and eigenvectors, which you are experts at now, provide the key to understanding the long-term behavior or evolution of a dynamical system described by this difference equation. X sub k plus 1 equals a times x sub k. Okay, so they talk before chapter, like at the beginning of chapter 5, if you look in your ebook, right before section 5.1, they talk about a kind of a general problem that that uses eigenvectors and eigenvalues regarding spotted owls. And you might want to look at that, but we're going to do a couple examples here today on this. The applications in this section focus on ecological problems to state and explain, say, than problems in physics or engineering, but dynamical systems arise in many fields. Okay, and they talk about undergraduate courses in control systems. So, my area of expertise is mathematical statistics. I can tell you, though, this is important for that field as well. Okay, they talk about the steady state response of a quote control system in engineering is equivalent to what we call here the long-term behavior of the dynamical system. So I don't know, has anybody ever heard of steady state response of a control system? Has anybody in our class heard of that, maybe in one of your other classes? Okay, well, it's always nice to be first, right? All right, that's fine, Christy, that's fine. Let me see, hold on, a few more responses. That's right, James. Steady state. James says steady state occurs after the system becomes settled and at the steady system starts working normally. Okay, so James has seen this, and actually, steady state also, if you take differential equations, Math 282, which incidentally I'm teaching next semester, they also, I know, like the forced responses and so forth, that comes up in DiffEq. So, and, steady state. So very good. Thank you. Thank you. Excellent. So, all right. Well, so we move down a little bit here. We go a little bit forward here, and this is an important piece of information. So I'm going to just kind of highlight this here. You've seen a little bit of it before, but if you assume that A is diagonalizable, meaning A equals P times D times P inverse, and you have linearly independent eigenvectors and eigenvalues, remember, you can have like a basis for a space Rn. You can have, I mean, like for R3, the standard basis is the E1, E2, E3 vectors, I, J, and K. But you don't have to use that as a basis. You can use another basis. And one thing you could do is if you have a 3x3 matrix that's diagonalizable, you will get 3 linearly independent eigenvectors. You've seen that in your homework, right? And those eigenvectors, hey, they live in R3. You have 3 of them. They could be an eigenbasis. They could be a basis for R3. So any vector, what they're saying here then is that any vector in your space can be written as a linear combination of the eigenvectors. Okay, and the decomposition of x naught determines what happens in your sequence. So like for instance, if you have x1, okay, x1 is equal to A times x sub 0. Okay, well, we would multiply the matrix A then times, and I want to take out a little bit stuff here. We would multiply the matrix A times the linear combination of eigenvectors you see here in equation 1. So if you do that, you will get this result, C1A V1 plus C2A V2 plus all the way up to Cn Avn. But remember, V1 is an eigenvector, and A times V1 would equal lambda 1 times V1. And, you know, A times V2 would equal lambda 2 times V2, and so forth. So what happens is you're able to write the, I'm trying to take out a little bit of the highlight here. The x1 is equal to that linear combination that you see there, C1 lambda 1 V1 plus C2 lambda 2 V2 plus all the way up to Cn lambda n Vn. In general, like if let me ask you, if you had x2, let's say you had x2, all right, what would x2 equal? X2 would equal A times x1, and that would be C1 times lambda 1 squared times V1 plus C2 times lambda 2 squared times V2, and so forth. So in general, okay, I'm going to say this right. The x sub k, okay, which is, I want to say this the right way. Trying to see if they give, well, I'm fine with that. I'm looking for terminology, but x sub k vectors give information about a system as time denoted by k passes, as it k months, k years, k day, k days. But x sub k can be written as this linear combination of eigenvectors for k equals 0, 1, 2, and so forth. I mean, it's a very beautiful thing. It's a very, very beautiful result. And you know, we of course are interested in what's going to happen as k goes to infinity. Okay. All right, so are there any questions on this? I mean, we're going to get to an example, but are there any questions on this this idea before we move to the examples? It's really quite beautiful because you're using all your linear algebra knowledge. The fact that x sub 0 can be written as a linear combination of the eigenvectors is true because the eigenvectors form a basis for the space they live in. And you know, and then you got the definition of the eigenvector, an eigenvalue being used. It's just, you know, it's great. Okay, well then let me go ahead and stop sharing with this if we're okay. No questions? Okay. Well, then let me get an example here. Let me upload an example. So let me get it here. Let me see. I got to pull it out of my 284. One moment, class. Yeah, here we go. Okay, we'll give it a moment to get uploaded. Excellent. Okay. Let me see. One moment here, class. Yep, that's what I want. That's what I want. Okay, so this, of course, is not an English class, but you do have to copy the example down. And, you know, how many feel that when they copy an example down, it helps them remember the example better? It kind of becomes a part of them better. Yeah, Sega knows what I'm talking about. Ryan understands. So, you know, let's take about 5 minutes, give you a chance to copy this example down. Binyam, Solomon agree. All right, so I'll give you like 5 minutes here. Okay, so of course I'm right here, and I saw. Okay, yep. Well, Christy, I know, I understand. All right. Christy, it's better to copy it down, but I'll leave that up to you. I'll leave that up to you. Okay, all right. So let's go ahead here and look at this question. Now, here you're letting your vector x represent two populations, owl and rat populations, where k is the time in months. Okay, so, and OK, O sub k is the number of owls in the region studied, and R sub k is the number of rats, and the rats are measured in the thousands. And what we're doing here is we're saying that in the k plus first month, the number of owls is equal to half times the number of owls in the previous month, plus a fourth times the number of owls, the number of rats from the previous month. So let me ask you these. So they took some data. Biologists in the field took data, and they came up with this model. Now, would it make sense that the number of rats in the k plus first month would be, the number of owls in the k plus first month would equal a half times the number of owls in the previous month? Would that make sense? Yeah, it makes sense. It certainly makes sense. Now why don't they say, could we say that O sub k plus 1 equals like 1 times O sub k plus 0.4 times R sub k? I mean, would that make sense to say? And I'm not really asking you right now to worry about the 0.4 R sub k. I really want you to focus on this part. I mean, we're saying that the number of owls next month is going to be dependent on the number of owls and the number of rats this month. But would this model here make sense if we put a 1 in front of the O sub k? I mean, is that possible? Sega doesn't think so. Mikkel thinks it's possible. Okay, this is what I'm looking for. Binyam's right. If no owls died or migrated away. But this is not really realistic, because we know there are going to be some owls that die and some owls that migrate away. So I'm trying to, you got these numbers in front of the variables, and there should be a degree of comfort. What about the 0.4? Now they have a positive 0.4 here. They have a positive 0.4. And it's positive. Could we instead have a negative 0.4 in front of the R sub k? I mean, would that be all right? In other words, what I'm saying is, to be clear here, could we say that the number of owls next month living in the region equals 0.5 times the number of owls this month? And I assume with a half, it must mean there's a large migration. I mean, it isn't like half the owls die in a month. So, and owls migrate, right? They migrate. They got to look for mates, things like that. Maybe find food. But would Would this be a reasonable model? Sega thinks it could be. So in other words, the more rats there are, that's going to make this a bigger negative number. The more rats there are, the less owls there would be. The more rats there were, I'm going to say this right. The more rats there are this month means less owls next month. That's a contradiction, because why? What do the owls do to the rats? They hunt the rats. So if there's a lot of rats around, that's going to help the owls. So, of course, that wouldn't make sense. But now if we look for the number of rats next month, that will be negatively affected by the number of owls. That's why you have a negative p, and p is 0.104. And then you have a 1.1k. So the 1.1 is kind of a big number. That's kind of a big number. So why is the 1.1 there? What's that telling you about the rat population? If the rats next month, I mean, why would the 1.1 be there? The birth rate. Okay, good. Okay, Mikkel, that's right. The birth rate exceeds the death rate. You got to be a little careful about saying it that way, but definitely it has to do with birth rate. So, okay, what we want to do is study the evolution of this system. We want to know what's going to happen eventually to the populations of owls and rats. Okay, and this is a simple model, a very simple model, but we might be wondering if these are, like, let's say these are a certain breed of spotted owls. Okay, what's going to happen to them eventually? Are they is the population going to grow? Are the owls destined to go extinct in time? Do we need to take some action? That sort of thing. Okay, so let's go ahead, and we want to find the eigenvalues and eigenvectors of the matrix A. Now, so remember, if I go back here, remember what we're doing here. Where we have that hold on here. We have that the number of owls next month is equal to a matrix A times the number of owls this month. You could also interpret this as the number of owls this month is equal to a matrix A to the number of owls last month. Okay, let's see, hold on. Yeah, right. So where am I gonna, and this matrix equation here represents this system of equations. So how am I going to find the matrix A? What composes, A here? What's going to be the coefficients? Right. Okay, so what's the first number? 0.5, good. Next number over here, 0.4, good. And then P is negative 0.104. And then finally, the last one is 1.1. So are there any questions on how we get the matrix A? Okay. Okay. So what do we have to find for this matrix A? What do we have to find? All right, Matthew has a question. So Matthew, what I did was I wrote down the matrix A. And the matrix A is based off of the coefficients of your variables. That's exactly right. That's exactly right. Great. So I have this matrix A. What do we do next? Got to find the eigenvalues and eigenvectors. Now, this problem actually is worked out in the book, and in the book, they just say, hey, the eigenvalues are this, the eigenvectors are that. We can use MATLAB in section 5.6 to help us find eigenvalues and eigenvectors. And what I've done here, is I've given you a MATLAB command that will produce nice eigenvalues and eigenvectors for this problem, but it won't necessarily do it for every problem. Okay, it won't necessarily do it for every problem. But what you do is you're going to store the eigenvectors and eigenvalues. Okay, you're going to store them in this. I'm going to say it the right way. You want MATLAB to get it's just like the LU factorization problem, where you have in brackets L comma U comma P equals LU of A. It's the same kind of thing. We want the eigenvectors and we want the eigenvalues, and the command is EIG for eigenvalues of symmetric A. Do not worry about why that is right now. The goal is to produce nice eigenvalues and eigenvectors. And for this problem, this command will work. And what you will get, well, we could try it here in MATLAB. We could try it. One moment. All right, so let me go ahead into MATLAB. And show you this. We'll come back to the example. We'll come back, but let me go into the MATLAB here, and you can do it on your end as well, right? So I'm going to do CLC. Oops, CLC, and there's a thing called clear. Okay, clear vars. See on the left side how I have these variables, and that's because I was working with MATLAB today. Well, if I do clear vars, I thought it would clear the variables. One moment. Just give me a moment here, class. One moment. One moment. There's a command I'm looking for. Let me see. Maybe somebody knows it offhand. Okay, hold on. I just want to find it if I can. One moment. You go ahead and type in the matrix A and type in that MATLAB command. Okay. Go ahead and do that. And I'm just bringing up a program from my DiffyQ class. Clear vars, that's it. All right, so let me exit that out there. Clear vars. I hit that. You see, it cleans out the variables, and that can be important sometimes. If you have old variables sitting around, it can mess things up for you. How many maybe have had that in a programming language where you had an old variable and it and you didn't want it really used, but the computer used it. Did anybody ever have that experience? Okay, Solomon knows what I'm talking about. Stale data, Binyam knows what I'm talking about. All right, so on that note, let me type in the matrix A. For section 4.6, you may use MATLAB for section 5.6, you may use MATLAB to help you get your eigenvalues and eigenvectors. Okay, so okay, so everything looks good here, and so the command is EVR, EVL equals I of sim A, and if I type that, see that? I got very pretty looking eigenvectors. I have an eigenvectors of 5, 1 and 10/13 and 1, very nice, and eigenvalues of 29. Now here's the thing, the eigenvalues are along the diagonal. So 29/50 as a decimal, that's 0.58, and 51/50 as a decimal, that's 1.02. Okay, so we'll go now back to the example, but are there any questions on what you're seeing here? Okay, all right, then let's get back to the example. Let me see here, back to the example. Okay, so then using that MATLAB command, okay, which worked for this problem, here are eigenvalues with their corresponding eigenvectors. Now what I did for the second eigenvalue, lambda equals 1.02, was the eigenvector, I used 10/13. So originally what you had for the eigenvector corresponding to 1.02 or 51/50, it was the eigenvector was 10/13 and 1. Okay, but generally I like to try to avoid fractions. So what I did was I just multiplied the 10/13 1 eigenvector by 13, and that's also going to be an eigenvector. Why is that? Well, here's a quick explanation. The definition of an eigenvector is that an eigenvector x is that a times x equals lambda times x, where x is non-zero, right? That's your definition of an eigenvector. Well, what if you were to multiply that eigenvector x by some scalar c, like 13, just like I did here? Would the scalar c times the eigenvector be an eigenvector? And it would. It would, because a times cx is equal to lambda times cx. It is a fact. It is a fact. Let me just see here. Yeah, it has to be because c is a scalar. Okay, so are there? Let me just see here. So of course, this is just, you know, c times lambda times x times the vector x. But then you can rewrite it this way. All right, any questions before we move to the next page? The 51/50 I wrote as 1.02. If you take 51 and divide it by 50, you'll get 1.02. And the 29/50 was, I wrote as 0.58. Okay, no problem. Are there any other good questions? All right. Well, now the question is, what do we do? What do we do with this? You know, how do we what, this is nice, but what's next? Well, what's next is to write out the x sub k. So after k months, the population x sub k, which remember, yeah, all right, hold on, let me go back for just a moment. Okay, very good, very good. So after k months, the x sub k, which remember stands for the population of owls and rats, in the kth month, after k months, it's going to be equal to this this linear combination of the eigenvectors, where k goes from 0, 1, 2, and so forth. And you'll notice that we did not solve for C1 and C2. Those are just unknown constants. Of course, if I were given an initial population of owls, an initial population of rats, then I could solve for those constants. But they're really not. We really don't need to solve them in order to determine the evolution of the system. So now what happens? What happens is as k gets large, and I just wrote down here that x sub k is, you know, the vector where we have the number of owls and the number of rats. I just thought it was good to put that there. All right, x sub k, when k gets large, is going to be approximately equal to C2 times 1.02k times the eigenvector 10/13. Okay, and maybe what I'll do here also, just to kind of emphasize things, this was, hold on, yeah, this is lambda 1, this is v1, eigenvector v1. Here's eigenvector lambda 2, eigenvalue lambda 2. And this is eigenvector v2. Okay, so as k gets large, they're saying that this part of your vector expression goes away. I mean, what they're saying, as k gets large, what does that approach? Okay, Binyam says he thinks it approaches the zero vector. Okay, well, that's true, it does. It does approach the zero vector. Certainly does. But why? What's causing that to happen? Why would that term approach the zero vector? Oh, okay. Robin says it's that factor 0.50a to the kth power. That's exactly right, because when k is large, I mean, try on your calculator. Hey, let's pretend k is 100. On your calculator, take 0.58 and raise it to the 100th power, and you're going to get, I mean, I get on my calculator 0.58 raised to the 100th power is 2.2 e negative 24. That's scientific notation. That's 2.2 times 10 to the negative 24th power. Sorry. Okay. That's a small number. It's so what this means is that eigenvalues that are less than 1, when k gets large, the portions of the solution where that involve eigenvalues less than 1 go to the zero vector as k gets large. And they don't have a role in the evolution of the system. So, I mean, are there any questions up to here? Are there any questions up to here? Let me ask you this. What if both eigenvalues were less than 1? I mean, our second eigenvalue, lambda 2, is 1.02. But what if we had two eigenvalues both less than 1? What would happen to the population of owls and rats if both eigenvalues were less than 1? That's right, Benjamin. They would go extinct. Extinction. That's right. So, very good, Solon. Very good, Robin. That's right. Very good, Matthew. And of course, that's a concern. So these endangered species, okay, you can imagine that they do studies like this, and if they're seeing that, hey, that based on linear algebra, my eigenvalues are all less than 1. The population is going to go to extinction. Then they have to make policy decisions so that that doesn't happen. Okay, I mean, you don't just pick a species and say, hey, I'm going to protect, yeah, well, there's a lot of things and of course this doesn't involve, Benjamin, there could be, yeah, the ecosystem. I mean, all this matrix A came about from like data, and of course it's a very simple matrix, but you'd have a much bigger matrix if you had like more interacting populations and so forth and other factors, and you can even base these populations on time. Okay, and it can be very interesting. But for now, yeah. So for k large, for k large, this means after many months, the population in the k plus first month is going to equal. There's going to be I should say that's approximately equal to C2 times 1.02 k plus 1, k plus first power, times 1013. But what I can do is I can rewrite this scalar, C2 times 1.02 to the k plus first power, as 1.02 times C2 times 1.02 to the kth power. I can do that. But then, when I do that, why would I want to do that? Well, what is this here, what I have circled? What is C2 times 10.2 to the kth power times the vector 1013? What does that equal? equals x sub k. That's right. By virtue of this. Oh, hold on. Let me use my little. Oh man, hold on. Let me do it again. One moment. So this, based off of this, we get that that's x sub k. So now, you see, we can do some interpretations. First of all, eventually, the number of owls and rats will grow by a factor of 1.02 each month, which is a 2% monthly growth rate. So that means that the owls and rats are not going to go extinct. They're going to grow, but it's a small growth rate. But 1.02 means like if it were 1, if this 1.02 were 1, what would that mean about the population of owls and rats? What has it done if the population, if that coefficient is 1? It's stabilized. There's no growth. It's just stabilized. It's 0% monthly growth rate. It's just unchanged. That's right. That's how I like to think of it, Solomon. Okay. Now, also, eventually, we can say that for every 10 owls, there will be 13,000 rats, because rats were in the thousands. Okay, and hey, maybe that's a little bit much for the rats, but I don't think so, because other animals are going to eat them too. But the 1013 comes from the eigenvector. See, the eigenvector also has importance. Just like the eigenvalue has importance, the eigenvector has importance. So that's right, Binyam. That's right. So, because what's happening is, this, say this the right way. Well, are we okay with this for eventually, it's eventually, for every 10 owls, there will be 13,000 rats based off of the eigenvector? Are we okay with that? This is, yeah. Are there any questions? Matthew's comfortable, Ryan's comfortable. Are there any questions at all? Okay, how many think Mikkel likes it? How many think this is pretty cool? Pretty cool stuff. Okay, Robin likes it. Solomon, yeah. This is good. This is great stuff. This is great stuff here. So let me do one thing here. One moment here. Okay, let me do one thing. What I want to do is give you a little time to work on this, maybe like 20 minutes of class time. And then towards the end of class, we'll talk about the MATLAB assignments. But let me just put a setting in here, because I want to make this. So I mean, I have to still get the section 5.5 exercises ready, and you know, those, you know, will be. I mean, I have to get the due dates for those. Likely, maybe at least maybe one of them would be due next Tuesday. But let me just hold on here. One moment, everybody. Okay. So if you bring up your MyMathLab, why don't you take a little time to work on your section 5, on these section 5.6 exercises? William's saying, very important. Yeah, when we look at the effects of climate change on populations, yeah, and so this is important. This is important. It is an important topic. Absolutely. So I'll tell you what. Let's take about let's spend about say 20 minutes working on the section 8.8.6, or at least till 8:20. Okay. And then I can talk about MATLAB assignments. So please stay in the class session, and let me stop the recording.